Okay, this is a continuation of our basic statistics that we started looking at in week 3. Statistics always begins with the premise that there is no relationship between variables. This is what is known as the null hypothesis. It's sort of a backwards way of looking at things, particularly from a business or research standpoint when we are actually looking for relationships, looking for correlations. In other words, in statistics, it's impossible to prove that something is 100% accurate or true or probable, but it is not impossible to demonstrate that something is likely to be not true. Note the term likely there. Last week we mentioned two types of inference, the confidence interval and tests of significance. Inference is based on sampling distributions and require a probability model for all data. And what we need to have is kind of confidence that data is from randomly selected experiments, collection processes, and that sort of thing. We want the data to be pure, so to speak. Here's an example. Survey asks randomly 2,500 adults if they agree or disagree with the following statement. I like buying new clothes, but shopping is often frustrating and time-consuming. Of those, 1,650 said they agreed with that basic statement. That is a basic statistic, P, and from that, we can generally infer that 66% of the population does not like shopping for clothes. They like to buy clothes, but shopping's a pain. Another thing we do with statistics is look at the shape of the distribution. Ideally, shapes should always be kind of bell curved, although that's not always the case. You might have certain product sales where your distributions of a given product are high among younger people and older people, but medium-aged people, say between 20 and 50, are not likely to buy the product. I can't happen to think of what that might be, but you can visualize that that would give you an uneven distribution. There's nothing wrong with uneven distributions. It's just they're a little less common. A variable x has any normal distribution with a mean and standard deviation and kind of looks like this formula here. Actually, it does. That is a formula for a normal distribution. These kinds of notations aren't really important for this course, but it's always important to kind of know where you can go back and find these sorts of things. And I point you again to the online statistical textbook that we have. Here's a standard bell curve, and what you can take from any bell curve is that 100% of the observations for a sample are within that curve. 98 or so will be between to the right of that line or to the left of the second line. That basically means that everything should be distributed closer to the center than in those two tails. You see the Z 1.2 down below the area where the blue and the white divide. That indicates that that point is at 1.2 standard deviations to the right of the true mean, which is indicated by the very top of the curve. A z-score of 0 would be the mean. Scatter plots are an ideal way to look at relationships between different variables. You look for positive associations. Two variables are positively association when above average values of one occur in individuals with above average values for the other. two variables are negatively associated when the opposite is true. However, negative association is not necessarily a bad thing. In fact, it's not. What is kind of the thing that indicates no relationship is a zero association. Associations are always measured as +1 at the high end, that as a correlation, or -1 at the low end. So correlations are always in between +1 and -1. It's often useful to have an association between your variables. Not always. Sometimes you don't want to see associations. Sometimes you don't want to see connections. But generally, you are trying to test something, and so you want to see an association. If you want to demonstrate that regular attendance in a typical on-ground classroom where students come 30 times per semester, and you're trying to see a relationship between class attendance and test scores, you will probably assume and try to prove that there's a linear correlation where students that only come 18, 20 times are proven to get lower test scores or lower scores on other assessments, just say. You might want to demonstrate that if you spend more money on advertising, your sales will increase. So you are looking for correlation, a correlation coefficient that in a lot of cases you want it to be positive. Again, though, sometimes a negative coefficient is what's called for. You look at things in the opposite direction, from the opposite standpoint. Always remember, though, that correlation does not imply causation. It's the whole notion behind statistics and statistical analysis that we are only studying probabilities. Correlation is indicated by this notation R. As you guys know, in statistics, there are a lot of letters that are associated with statistical concepts or mathematical ideas, and it's hard to keep track of them all. But R is the way we indicate correlation, and R is always between 1 and -1. An R that's greater than 0 indicates a positive association. R that's less than 0 indicates a negative association. And remember, I mentioned this a couple looks back, values near 0 imply a very weak linear relationship. Key thing to remember here. So what do plots look like? Scatter plots, you guys have seen these. Most of you, especially those that have had statistics classes. Here we have 4 plots. The one at the top left, lettered A, shows a correlation of 1. That means you're measuring a variable on the left with an explanatory variable going horizontally along the bottom, and you see a 100% relationship between whatever's being tested or whatever's being looked at. On the top right, we see a somewhat negative correlation. The coefficient for that one would be about 0.5, minus 0.5, excuse me. Looking at C, the bottom left, you see a pretty strong relationship between your tested variable and the explanatory variable along the bottom axis. So that has a correlation coefficient probably around 0.75, 0.85, or thereabouts. And then look at D. D at first looks like it's kind of random and that there might not be any relationship. But there is, in fact, a slight, very slight relationship, a coefficient of 0.15 or 0.1. Very small, but still provable ever so slight correlation. These are some of the things that we use computers for. The key takeaway from this video, which kind of goes with last week's second video, is probably the whole notion of coefficient between +1 and -1, and its relationship in importance in showing correlation between variables. Anyway, that's it for this one.